good evening, everybody. So now we're again changing the topic quite a bit, and we're going to talk a bit about climate change in the Arctic in general, and then we're going to talk about these gases. So it will be some different things, and all of these pictures here in the screen, they are items that I worked with. Okay, let's start having a look at the atmosphere and what it contains. So most of it is nitrogen and oxygen, and these are gases that are not that important for our climate. Then we have the greenhouse gases. You have all heard about CO2 and methane and the laughing gas N2O. They have quite high concentrations that are increasing, and the lifetime is quite long. This means that what we release to the atmosphere, it's not only our problem, but it's a problem also for our children. What I'm going to talk about today is this lower box here with all sorts of trace gases that are present in very, very low concentrations and that have a very short lifetime. So they are gases that are very difficult to measure because of the low concentrations and the short lifetime in the atmosphere. And you could think, what is the relevance then, because they disappear so quickly? Some of them disappear actually within minutes, so they surely are quite reactive. This group is called biogenic volatile organic compounds, and it's containing thousands of different compounds, maybe 30,000 different chemical molecules. And you have sensed these chemicals when peeling a citrus fruit or when having a walk in the forest. So it's these nice smells of nature among other compounds. And actually, even though they are normally invisible, you have sometime actually seen these compounds. If you've been in some mountainous area, this you cannot experience here in Denmark, I'm afraid. Sometimes on top of mountain forests, you can see this blue haze, and that is formed of these VOCs when they mix with man-made pollution and react in the atmosphere. And this haze is then causing the Smoky Mountains. And these kind of things have been used in politics as well. So for example, Ronald Reagan actually correctly said that forests are releasing more VOCs to the atmosphere than we are. About 90% of VOCs that come to the atmosphere are coming from nature, and only 10% from anthropogenic sources. So when these gases get into the atmosphere, it leads to complex reactions, and we're not going to go into that, don't worry. We can just look at the end products here. So one of the end products of VOCs is ozone. And ozone is a toxic pollutant and causes, for example, respiratory diseases in humans and decreases photosynthesis and crop yields in plants. VOCs also stick together and on surfaces of small particles in the atmosphere and form aerosol particles. So these aerosol particles that are shown by these dots here, they can also stick together and form clouds. Both clouds and aerosol particles reflect sunlight, and in that way they can actually cool the climate. So in this way, VOCs can actually reduce the climate warming a little bit. Then let's move to the Arctic. And when I tell people that I work with Arctic, this is what they imagine. So I'm asked, okay, where is it that you go and get those ice cores? And actually, I don't work with ice cores, but this is the first image that comes up in Google if you Google the Arctic. So this is what the Google also thinks. But this is more like the Arctic that I work in. This is actually taken in northeast Greenland, in the most extreme Arctic, the high Arctic. And this is the Zuckerberg research station, close to where Sirius Patrol has their base. And here, if you zoom into the landscape, you see that it's actually covered with plants that are very fast growing and lots of flowers there as well. Some places it's very barren and small plants, and in other places the plants in Greenland also grow quite high. So forests are releasing VOCs, and actually this is also taking place in the Arctic. The plants there are a source of VOCs to the atmosphere. And this is getting more intense. So when the climate is warming, the vegetation is changing in the Arctic. So these photos were taken in the same spot in northern Sweden, and you can see that in some decades, the landscape from open tundra has changed into higher bushes and even some trees growing around here. And that's something that we see when we do field work with bare eyes. And it's not always that cold. If we take the air temperature, that might actually mislead you. This is a photo that was taken just a day after the snow disappeared when we were doing fieldwork on Disco Island in Greenland. And air thermometer showed 14 degrees, but it was really, really hot. The tourists were hiking by in bikini, and we were sweating while we were working in the field. So often the tundra surface is about 10 degrees or more warmer than the air temperature shows. So this is also something that's in the past led the modelers totally wrong, because they use the air temperature to predict the release of gases from the ecosystem. And that's not all. You all have heard about climate change, but I don't know if you've heard that it's not equally distributed across the globe. So the Arctic areas are warming much faster and much more strongly than the rest of the globe. And there are several reasons for this. For example, the decrease in ice that is reflecting a lot of radiation away is replaced by darker surfaces that retain the heat better. So my group has attempted to study how this climate warming in the Arctic affects the release of VOCs from the tundra ecosystems. And how we do this in practice is doing field measurements. So we put this box on top of the area that we want to measure, and then we circulate air through the box. And from the outgoing air, we trap the VOCs into filters that we bring back home and analyze in the laboratory. And we can cheat the nature to think that the climate has changed. So we use different manipulation experiments where we mimic changes in climate. So we can, for example, use snow fences like here to get the snow pile up on one side of the fence, and then we can compare that side to the other side and see how increasing winter precipitation would affect the ecosystem. Or we can have this shading tent on top of an area to see how increasing cloudiness would affect. Now I'm focusing on temperature, and for temperature increase we use these open-top chambers that are sort of like greenhouses with open top, so that rainwater gets in. And we start with an experiment close to Nuuk in Greenland, where we had this reduced sunlight treatment and warming treatment that were compared to control. And all of these we have replicated 6 times. So in this site, some of you may be interested in plants. There are 2 kinds of plant species that dominate the community. So there is willow, peel, and crowberry, heuling, that are dominant species there. And we measured VOC release from this whole mini ecosystem in outside and inside of these open-top chambers that warm by 2 to 3 degrees. This graph here shows the release of VOCs during one summer. So we started in Arctic early summer in June and ended in August. And then we had measurements at different time points. And what we saw was that consistently the warming treatment had much higher release of VOCs to the atmosphere than the control. And when we sum up the whole summer's measurements, we could see that actually there was a threefold increase in the release of VOCs. It was quite a drastic effect of just a couple of degrees increased temperature. And in this place, we did measurements also on the two species of plants, so the willow and the crowberry, and we could see that both of them had a similar response, while soil alone didn't have this response. So we could point that it was the plants that were causing this large increase. We've done experiments like this in different places during the years, the past 10 years or so, and what we've noticed is that regardless of how long the experiment has been running and what kind of an ecosystem it is, we get a large increase from doubling to tripling and more in response to 2 to 4 degrees increase in temperature. So this means that the release of VOC gases to the atmosphere is likely to increase much in the near future in the Arctic areas. So I said that soil didn't respond very much to the warming, but still we're going to have a little look into the soil as well. And when we talk about Arctic, we cannot not talk about permafrost. And let's have a look at this map first. This map shows different areas that are at the moment covered with permafrost. And permafrost means frozen soil that is frozen minimum 2 years in a row. And we predict at the moment that these red areas will be completely permafrost-free year 2050, quite soon. There are drastic changes going on. And the orange areas are predicted to lose all the permafrost by 2100, whereas the yellow areas will still have some permafrost left. And what happens when permafrost thaws is presented in this graph. So if we start from here, this is sort of the situation now. So plants are taking up carbon from the atmosphere, and plants and soil microbes are respiring and releasing CO2 to the atmosphere. And then we have this freezer down here, this frozen soil below the topsoil that melts during summer and freezes every winter. So the topsoil is not part of the permafrost. The permafrost is lying here deeper down. So when the temperature increases, the topsoil gets thicker and the permafrost shrinks. And what happens then depends very much on if there's a lot of ice in the permafrost. If ice melts, it will become water, the area will become wet, and plants will probably like this and grow better. Then the plants will take up more carbon from the atmosphere, but more carbon will be also released from soil to the atmosphere. And in the long term, what is expected is that the soil will start releasing more carbon to the atmosphere as CO2, and if it's waterlogged, as methane. And this is the reason why some people say, don't wake up the sleeping monster. It can have drastic effects on our climate. What we wanted to do, of course, in our group is to look at if the thawing permafrost is also releasing other gases than CO2 and methane. So we set up this experiment with fancy automatic valve switching and containers with frozen soil that had been frozen for thousands of years. We brought these soils frozen back to Copenhagen, and then we started this experiment where we measured gases while the soil was thawing. And we also had containers where we had the topsoil in the same containers. That's important to remember. This is a screenshot from the computer when we analyzed the VOCs in real time. So this is the time series, and we are switching from different container to container. And here we come to a permafrost sample, and you can see that some of these curves are really going up. A lot of gases are released from the permafrost. As a matter of fact, more than 300 different molecules were released. What we also saw was quite surprising, and it was that when we had this topsoil in the same container, the amount decreased drastically. And that was a really surprise that we didn't expect at all. So here it's illustrated in different way. All of these symbols here show release of now two gases alone, ethanol and methanol. And you can see that permafrost releases much larger amount alone than when we have the topsoil in the same container. So the gases disappeared somewhere. What happened? Did the microbes have a party there with the ethanol and other stuff? Or did the compounds get stuck into the soil particles, or what happened? We did this additional experiment where we used radioisotope labeled VOCs that were specifically fabricated for us. So we put soil into containers again, and then we used these labeled compounds so that we could follow where the label ends. And what we followed was whether it becomes CO2, and we could use this method to calculate if the microbes are degrading the VOCs, if they are eating them. And what we noticed was that they in fact were. So nothing whatsoever happened in sterilized soil where we had killed the microbes. So the compounds didn't get stuck in the soil. In fact, the microbes used some of these compounds super fast, and we could also see that permafrost itself also started to have this activity just a little bit slower than the other soil samples. Now, at the end, I'm going to take more a helicopter perspective to the whole thing. And this is, as a matter of fact, a photo from our field campaign where we brought the same expensive instrument as in the permafrost study out to the field. And you can imagine how I felt looking at this instrument that costs more than 1 million kroners, hanging from this thin thread in the air and landing with a bump in the ground. But it survived, and we're getting some interesting results from these further studies. In these studies, all in all, we attempt to understand how the plants here on top of the soil respond to climate change, how the soil processes where we both have release of compounds, but now also uptake, we realize, and how also new things like insects that are feeding the plants impact this thing. And we're also going to work globally in alpine tundra systems. And the next step is to improve the models that we have to predict VOC emissions in the future, and to put on top of these chemistry climate models to try to understand what does it actually mean for our air quality and climate. Does it affect the ozone concentrations or amount of aerosol particles in the atmosphere? Thank you very much for listening.